Okay, thank you so much for everyone who's here for GOCC this week. Today we have Pranav, who is a student at UC Berkeley, telling us about clasped web bases for SL4 invariants of tensor spaces. Before we begin, let's go over a community statement. We are all learning. Everyone has something to contribute, and no one has all the answers. So with that, take it away, Pranav.
Okay, thank you so much for the invite. I want to start off by apologizing for my voice. I felt quite sick last night, so if I sound kind of off, that's probably why, but we move. Yeah, so I'm going to talk about web bases for tensor invariants. This is joint work with my advisor Christian, and so I want to tell us about the basic setup. So I'm going to start with the Lie group SL sub R, right? We're only going to consider low rank cases, so R is going to be 2, 3, or 4 for me in this talk. But so SLR has this natural R dimensional representation, which I'm going to call V. This is the defining representation. And the kinds of representations I'm going to consider now are, well, I take exterior powers of V and then take tensor products of these guys. If you know a bit of Lie theory, these are like the fundamental representations of SLR, and then I'm taking tensor powers of these fundamental representations. And the main goal for me is to describe the invariance in this representation. So SLR acts on this tensor product. I want to see which vectors are left invariant, right? So kind of a special case of this is, so if I pick all my exterior powers to be the first exterior power, so it's just V itself, then this tells me something about the coordinate ring of the Grassmannian. So this is some geometry if you're geometrically inclined. But yeah, I'm not going to be talking too much about geometry this time. So some history, I guess, is, well, this is like invariant theorists have considered this sort of problem for super long, and the motivation for like this talk comes from the work of Kuperberg in the 90s, where he gives a nice diagrammatic presentation for these invariant spaces. So this is some subspace in this tensor product, and Kuperberg gives a basis for the subspace in terms of planar graphs, and he calls it the non-elliptic web basis, and he does this for r equals 2 and 3. And since the 90s, there has not been much progress to like extending this to higher rank until in 2025, Christian and collaborators extend this to SL4. And they had to like introduce a completely new combinatorial framework to do this. So this is like a genuinely hard problem to find nice diagrammatic bases for these invariant spaces. So I'll be sort of like walking you through what these bases look like, what Kuperberg's basis looks like, what Christian's basis looks like, and then eventually we're going to get to clasping. But I want to start off with like, the really classical thing, which is SL2 webs. And you should really think of this as you have n vertices on a circle, and then you look at non-crossing matchings of this, right? And there's Catalan number many of these, but this is what an SL2 web looks like for me, right? So how do I interpret this as an element in my vector space? So because SL2 has this special property that V is its own dual, this works only in SL2, but because I have V being its own dual, I can pair two copies of V to get a complex number. The way that works is you have two-dimensional vectors, you put them in a matrix, you take the determinant. That's one way to think about this evaluation map. So what this picture is telling me is it's telling me which two vectors I'm pairing up. So for example, here I have an invariant of the sixth tensor power of V. So I have 6 copies of V. And this picture is telling me that I evaluate the first with the second, the third with the sixth, because that's where the strand goes, and the fourth with the fifth. Right? And every non-crossing matching gives me one such element. And turns out that this is a basis for my entire invariant space. So this is also called the temporally Lieb algebra, and this was known very classically since like the 30s or the 40s. Okay, so I think a better way to think about SL2 webs is actually not as invariants, but as morphisms, right? So if you look at this web, I could read it sort of left to right, where I think of my vertices 4, 5, and 6 as being on the left, 1, 2, and 3 as being on the right. And I should think of this as a map from the threefold tensor product of V to another threefold tensor product of V. And caps correspond to co-evaluation, cups correspond to evaluation, whatever that means. But I mean, for SL2, V is its own dual, so you get these natural maps from the trivial representation to V tensor V, and also conversely. And just by some dualizing argument, you just get this sort of thing. So this Hom space is naturally in bijection with sending over the V tensor M to the other side, and V is its own dual. So that's what lets us think about these invariants as actually like morphisms. So if I think of this as a morphism from 4, 5, and 6 to 1, 2, and 3, the way I should think about this is, well, first I'm pairing the 4 and 5. So that's like this evaluation thing. And I'm co-evaluating at 1. So that gives me this factor. So this is like a cup and this is a cap. And the V6 just goes to wherever like B3 was. So this formula is basically telling you how to think of this as a map from the third tensor power of V to the third tensor power of V. So these are just some different ways of interpreting webs, but I mean, if you just care about the combinatorics, you don't really have to think about all the Lie theory behind this. And yeah, so here's the very classical theorem. I think it's by Roomer, Teller, and Weil back in 1932, where the theorem is that these non-crossing matchings, which I'm going to call SL2 webs, so that if you have n boundary vertices, each such graph gives you an invariant in the nth tensor power of V, and these graphs give you a basis for this invariant space. So this is also called the temporally Lie algebra. And if you just count dimension of this invariant space, if you know some Lie theory and you want to do some like multiplying Schur polynomials, you get that the dimension of this invariant space is the Catalan number. But if you just want to look at the combinatorics of these graphs, well, you have non-crossing matchings on n vertices, the number, or 2n vertices. So the number of those is the following, right? It's the Catalan number. So this was like very classically known, and this was Kuperberg's like starting point. But now I want to say a bit about clasping, because that's sort of like the main input of Christian and mine. So if you know some Lie theory, you know that there's a lot more representations of SL2 than just V. V is the two-dimensional representation. These are actually indexed by non-negative integers. So for every non-negative integer, you have a representation. For SL2, you can think of these as just taking symmetric powers of V. So if you take the kth symmetric power of V, this is going to be an irreducible representation, and I'm going to call that Vk. And this naturally sits inside the kth tensor power of V, right? The symmetric power lives inside the full tensor power. So anytime you have a sequence of positive integers, so this is just Vk sitting inside V tensor k, but if I have a bunch of these non-fundamental irreducible representations, if they sum to n, you can sort of, well, this Vk1 sits inside V tensor k1 and so on and so forth. And when you tensor all of these, this tensor product of non-fundamental irreducibles lives inside the nth tensor power of V. Right? And this, I mean, if you just dualize, because invariants are just maps into the trivial representation, so I get a map going the other way, which is going to be a projection. So sort of the motivation for this is the classical story tells us a lot about fundamental representations. So if I just look at V and look at tensor powers of V, I understand exactly what the invariants there look like. But you could generalize to arbitrary irreducible representations. There's a lot more of those. And we want to understand what these what the invariant spaces for these look like. So in particular, I have this nice basis for just fundamental representations given by non-crossing matchings. So that's like a basis for the space on the left of this invariant space on the left. I could ask about what happens to this basis under this projection map. And so the nice answer is some of my basis elements are going to map to 0, but the ones that don't map to 0, turns out they give a basis for the space on the right. So if you're here to look at just the graphs, this is what a clasped web looks like. I have these clasps on the outside, which are just telling me which boundary vertices I should clump together. So this is just like a regular web, or like non-crossing matching with the extra decoration of the clasps on the outside. And the sizes of the clasps tell me which tensor product of irreducibles I'm considering. So I have a clasp of size 3 because I have 3 boundary vertices, so that corresponds to V3. And then I have a clasp of size 1, so that's just V or V1. And then I have a clasp of size 2, so that corresponds to V2. So this picture is a clasped web for the invariant space V3 tensor V tensor V2. Okay. So Kuperberg in the 90s comes along and answers this question of which of these non-crossing matchings actually project to non-zero things under this projection map. And here's his theorem. So you look at the clasped SL2 webs, and you only pick out those non-crossing matchings which don't connect two vertices within the same clasp. Right? These form a basis for the invariant space. So what do I mean by this? So in this picture, if you look at this large clasp with 3 boundary vertices, there's 2 adjacent vertices that are just connected within the same clasp. This is what Kuperberg calls a U-turn. And anytime you have a U-turn, this is bad. So this projects to 0 under this projection map that I have, this projection map pi. So Kuperberg's theorem was if you just look at the subset of webs which don't have U-turns, then those form a basis for this invariant space. And he calls this condition non-convexity for higher rank. So he also answers this very same question for SL3 representations. And there, the condition is slightly more complicated than just not having U-turns. Yeah. Okay, so that was the SL2 story. That's like as simple as it gets, but like the SL3 picture is like a lot more complicated. So this is the bulk of Kuperberg's paper in 97 is talking about SL3 and also the other rank 2, the algebras. But here's where we get a lot more interesting graphs. So from here on out, I'll try to define things a bit more precisely, but a tensor diagram for SL3 is, once again, you have a circle, you have these boundary vertices, you draw a planar bipartite graph. So, oh, oops, actually, there's a typo. This shouldn't be planar because I have a crossing. I just look at bipartite graphs embedded in the disk. So I have black and white vertices, remembering my bipartiteness, and I just have any old graph. The only condition is the internal vertices all have degree 3. So if you zoom in on any internal vertex, you just have 3 sort of strands coming out, and all the boundary vertices only have 1 strand. So this is called a tensor diagram. And there's like a formula that tells you how every tensor diagram gives you an SL3 invariant. I don't really want to go into the weeds of this because I don't think it's super interesting, but the important thing is you just look at the boundary vertices and the colors tell you whether you're looking at V or V dual. So I have 3 black vertices, so those correspond to 3 factors of V, and 3 white vertices, so it's 3 factors of V dual. And somehow this graph is giving me an invariant in the space V tensor V dual, tensor V dual, tensor V, tensor V, tensor V dual. So an example, so like there's 2 fundamental building blocks of these. One of them is the pairing between V dual and V, because these are dual vector spaces. So if I have a V dual and a V, a strand between those two just corresponds to the pairing, right? Turns out this is an invariant of the SL3 action. The other example is the determinant. So if you have 3 vectors, 3 three-dimensional vectors, you can just stack them all in a matrix and take the determinant. That is also an SL3 invariant because SL3 only has matrices with determinant 1. So when you act by that, this number doesn't actually change. So these are my 2 fundamental building blocks. Every other tensor diagram just looks like some composition of these guys. Right? And as before, instead of thinking of invariant spaces as just, maps into the trivial representation, I could do this sort of dualizing game where I dualize this W2 factor, send it over to the other side, and then I can think of this as a more general Hom space. So it's a morphism between 2 SL3 representations. And the benefit of thinking of these this way is when you have two functions, if they're compatible, then you can compose them. And I want to think about composing these tensor diagrams. And on the level of tensor diagrams, I should think of this as just gluing two graphs together. So I'll have a picture somewhere, which I'll show you, but there's very classical invariant theory tells you that actually every invariant that you're ever going to get is going to be obtainable by gluing together these two fundamental pieces I told you about, which is pairing V with V dual and taking the determinant. So the fundamental theorem of invariant theory tells you that every invariant comes from just gluing these two pieces together. So this is what I mean by concatenating. So on the left, I have a tensor diagram, which I can just slice through the middle, and then I get two smaller tensor diagrams. And if you look at these two smaller tensor diagrams on the right, they both look like this determinant example I had. So the one on the left is straight up the determinant example, but the one on the right is slightly different, where now you have three copies of V dual, which you can think of as row vectors, and then you put the row vectors in a matrix and take the determinant. So in some sense, it's like kind of dual to the thing on the left. But I can think of gluing both of these. So these black and white vertices annihilate each other, and then you get the thing on the left. So this is what I meant by concatenating, like two tensor diagrams. And on the level of morphisms, this just looks like composing. So if you read your tensor diagrams left to right, you get a map. For each of these semicircles, you get a map, and then you compose both those maps to get a bigger map. So theoretically, that's what's happening, but on the level of graphs, you're just like slicing your graph in half, and then you get two pieces. And the other operation you can do with invariants is you can multiply invariants or tensor invariants, and what that looks like on the level of graphs is just, superimposing one graph on top of the other. So what is this example saying? So I didn't label my vertices, but I should start at the top right, call that one, and go, is that clockwise? Yeah, I go clockwise. So I have two copies of this determinant looking thing where I take the first, second, and fourth vertex. The three of those form a determinant sort of picture. So that's this first determinant, and the third, fifth, and sixth vertices form another determinant, and I'm just multiplying both these determinants. So this gives me an invariant of this six-fold tensor power of V. And graphically, what's happening is I just take two of these tensor, or like two of these determinant pictures, and superimpose them on top of each other. Okay, now I've told you that every tensor diagram gives you an invariant, but what happens in general is that there's way too many tensor diagrams compared to the dimension of this invariant space. So these are not all linearly independent. There's going to be a bunch of relations between them. And sort of the main relation is this uncrossing relation. So anytime you have two strands that cross each other, you can decompose it into a sum of like a formal sum of these two graphs. So what you can do if I give you any old tensor diagram is you keep applying this rule to resolve all your crossings. And ultimately, you're going to get some linear combination of graphs, but all of them are going to be planar. So whenever I say web from now on, I just mean a planar tensor diagram. So something without any crossings. So a remark is, well, we knew that all the tensor diagrams spanned the invariant space. That was the fundamental theorem of invariant theory. But this relation tells me that anytime I have a crossing, I can resolve that as well. So in fact, I don't have to think about all the tensor diagrams. I can only restrict to the webs, which are the planar ones. So now we know that the webs span my invariant space as well. Turns out even these are too many. So we're going to have to cut down even more of these to actually get a basis. Okay, so an example of the uncrossing relation work is, I have this crossing. I can break it up into, not crossing at all, and then introducing this extra pair of vertices. I could do a similar thing here. This is another example of uncrossing. So these two slides were there just for me to talk to the geometers at Berkeley. So this is one manifestation of the Plukad relation, if that's something you care about, which comes from the coordinate ring of the Grassmannian. If not, these are just some linear combinations of graphs, right? Okay, so Kuperberg's main theorem was if you want a basis for SL3 invariants, what you're supposed to do is you look at all the webs, so all planar tensor diagrams, but then you only look at those which don't have a two face, so you don't have like a bigone or a square. As long as you avoid both of these, you're gonna and you look at the list of all the webs that don't have a bigone or a face or a four face, these are going to form a basis for your tensor power. He also has a condition called non-convexity, and then he talks about more general tensor products. So once again, these are the non-fundamental irreducibles. So if you look at the non-fundamental um, irreducibles, he has an extra condition in terms of clasped webs. But I'll talk more about that once we get to the SL4 picture. Okay, so I want to pause here. Do we do questions during the talk? I'm not sure. Okay, so I'll pause here for questions. Okay, cool. I will carry on then. And so this is sort of like the content of Christian and his collaborators' paper is where they introduce this new kind of graph called an hourglass plabic graph. And this is the framework within which they're able to talk about SL4 invariants. And sort of just to let you guys know about the state of the art. So nothing is known about SL5 webs and higher rank. So this is very much like active work of Christian and others. But this is like a very, very hard problem as your rank increases. So SL4 is like the highest one to which we actually know anything. But yeah, so they define an hourglass plabic graph, very similar to tensor diagrams or plabic graphs, where you have boundary vertices, all of them have exactly degree 1, and all the internal vertices have degree 4. But my edges are of two flavors. I could have a multiplicity 1 or a multiplicity 2 edge, right? And multiplicity 2 edges, I'm not going to draw as two parallel strands. I'm going to introduce like a half twist in there, and I'm going to call them hourglass edges. So I'll show a picture on the next slide. This is an example of an hourglass plabic graph. So all my boundary vertices have, well, simple degree 1 in the sense that they can be connected to hourglasses. So you don't count boundary degrees with multiplicity, but you count internal degrees with multiplicity. So boundary vertices can be connected to hourglasses, like so. But if you count the degree at any internal vertex with multiplicity, they're all going to be 4. And this has to do with the fact that we're working with SL4. And this is supposed to give me an invariant of some ninefold tensor power of the different fundamental representations. So now let's talk about some of the combinatorial tools they use to talk about hourglass plabic graphs. So there's this notion of trips for regular plabic graphs as well, introduced by Postnikov, but I don't think it's I think it's best for me to just talk about this in the SL4 case. So we're going to take the more general case of hourglass plabic graphs, and I'll talk about what a trip is. So you start at any boundary vertex, right? So let's talk about trip 1. So trips come in 3 flavors. There's a trip 1, a trip 2, and a trip 3. So let me just talk about trip 1. So that's this purple thing here on the left side graph. So what you do is you start at a boundary vertex, and then you travel along the edges. But each time you hit a white vertex, you take a left, and each time you hit a black vertex, you take a right. Right. So you do this first edge, you take a left, then you hit the black vertex, you take a right, you hit the white vertex, you take the left, and so on and so forth. And you do this until you hit another boundary vertex. So you start at B6 here, and you end at B1. You could also do trip 3, which does the opposite. So at a white vertex, you go right, and at a black vertex, you go left. So if I do a trip 3 starting here, I go this way, and then I end at B9. So that's the green strand over here. And there's also these trip 2s, which sort of like are in the middle. So every time you encounter a vertex, you don't go left or right, you go down the middle, basically, because, I mean, anytime you encounter an internal vertex, there's like 3 options because the degree is 4 and you're coming from one of the directions. So you have 3 options. The trip 2 takes the middle option. And yeah, the orange and red lines here are the 2 trip 2s starting from B6. So these are just some paths or these are some walks along my graph. Okay. Now, the actual theorem about SL4 invariance isn't just saying, well, these graphs form a basis. You actually have to consider graphs up to some moves. So there's some local combinatorial moves, and graphs which are move equivalent are considered the same for our purposes because it turns out that they give the same invariant. So one of the moves I have is this benzene move because it sort of looks like a benzene where you have this hexagon and then you have these alternating double edges. The benzene move just says you can sort of switch which ones are single edges and which ones are double edges. So this local move gives me equivalent graphs. There's this more complicated square move, which comes in 4 flavors. But the way I think about it is anytime you have a square, you can flip the colors of all the boundary vertices of the square at the cost of sort of like elongating or contracting these boundary strands. So I mean, we're not going to use these crucially. I just think I should include it because I'm going to state Christian's theorem. So, and then there's this easier move, which is just a contraction move, which says if you have 2 hourglass edges next to each other, you can collapse both of them. And I mean, these look like random moves, but some combinatorial motivation for why these are the correct things is that these moves actually preserve like endpoints of the trip strands that I defined, which I mean, the trip strands also seem unmotivated if you don't like think about the Lie theory behind it, but I think it's a cool game to just look at the trips anyway. But these moves are the correct thing because these preserve the trips. Okay. Now, they define a web to be contracted if you basically do all possible contraction moves. So you don't have any pairs of hourglass edges. So anytime you see this, you collapse it. Such a web is called contracted. And they say it's fully reduced. This is sort of the analog of Kuperberg's non-elliptic condition, which said, there's no squares. The analog here is that there's no squares which contain an hourglass edge, but it's slightly more subtle than that. It says you look at every single web that's move equivalent to yours. So you apply all possible moves. And then you check that in each of these webs, you never have a square face which contains an hourglass edge. So this is a lot more of a complicated condition than Kuperberg's condition because in the SL3 case, I don't have any moves at all. So there's no like move equivalence sort of statement. And also I just have to look at squares. So if I'm given a web, I can just see if it has a square or not, and then I'm done. Here I sort of have to like explore this whole move equivalence class and then decide if if any of these move equivalent things has a square face with an hourglass edge. They also give a nicer way of checking if something is fully reduced without having to explore the whole move equivalence class. But yeah, so the set of contracted, fully reduced hourglass plabic graphs, I'm going to call CRG for contracted, reduced graphs. And their theorem is going to be that these form a basis for my invariant space. This was the remark that if you want to check that something is fully reduced just by the definition, this is like a really difficult thing to do because you have to keep applying all these moves, which are really complicated, and there's no like directionality to these moves because you could just do these moves in any order and they don't always commute. So you somehow have to explore this whole move equivalence class and then see if you ever get a bad square. Bad square being one where you have an hourglass edge in the square. But they have a better combinatorial criterion for this, which is the following. So they say that if you want to decide whether a given contracted web is fully reduced, you just have to look at the trips. So as long as your trip 2 strands don't like double cross, so they don't cross and cross again. And also like there's this condition on trip 1 and trip 2 strands. So if you have any trip 1 and trip 2 strands that intersect, then they sort of like travel together for a while and then they diverge and they never come back together. So this is just some combinatorial condition on these strips. So you just, given a contracted hourglass plabic graph, you just draw all the trips and then you just check these two conditions. And then if it satisfies both these conditions, you know that it's going to be fully reduced. So you don't actually have to check all the move equivalent things. And yeah, so this is sort of the remark that this is a much better way of checking fully reducedness. So this a priori really difficult sounding condition to check is actually not that bad if you just draw out all the trips. Okay, and now here's the theorem of Christian and collaborators. So for SL4, a basis for the invariant space. Once again, this is just the fundamental invariant, so it's just V's, V duals, and the second exterior power of V. So for SL4, there's three fundamental representations. I'll remark on this again. But the point is, if you just orient all your benzene faces in some preferred way, which they call clockwise, so because you can always rotate a benzene face, they just, and these are going to be equivalent, so they just say, well, pick your favorite orientation for all the benzene faces. Once you do this, the fully reduced contracted hourglass plabic graphs, these form a basis for the invariant space. Right? So yeah, the remark is you sort of have to pick this unique benzene representative because you could always just rotate and get the same invariant. But yeah. So a few words on how they proved this, because I think this is some cool combinatorics. What they do is associate to any web. So I'm gonna sort of like skim through all the details because I don't want to. Yeah, this is like very technical stuff, but for any web, they define this word, which they call the separation labeling. And what this does is using this word, this is going to be like a lattice word. And when you use this lattice word, there's this classical bijection between lattice words and Young tableau. And it is also known by, just multiplying Schur polynomials that you can use some cardinality of a set of Young tableau to find the dimension of the invariant space. So they just construct this bijection between webs to these lattice words. And these lattice words are in bijection with Young tableau, and these Young tableau are in bijection with the basis for the invariant space. So basically what they've done is they've shown that these contracted fully reduced graphs span everything, again by some analog of the first fundamental theorem of invariant theory. And once you have a spanning set, you just check that you have the correct number of things in the spanning set, so it has to be a basis. Okay, now I want to talk about clasping for SL4. So anytime you have a weight for SL4, so you have, or this works for general SLR as well. So you have these omega i's, which are the fundamental weights. So for SL2, there was only omega 1 that corresponded to V. For SL3, I have omega 1 and omega 2 corresponding to V and V dual. For SL4, I'm going to have omega 1, omega 2, and omega 3. So omega 1 is V, omega 3 is V dual, and omega 2 is the second exterior power of V. So these three are my fundamental representations. But any other weight, so all the irreducible representations of SL4 are parameterized by dominant weights, which are just, you take non-negative integral combinations of these omega i's. So there's infinitely many of these. But each V lambda corresponding to any weight lambda turns out sits inside a tensor product of the fundamentals. So if I want to understand these arbitrary irreducibles, I could always embed them inside some big tensor power of V's, V duals, and this second exterior power of V. And so if I have a bunch of these V lambdas, so V lambda 1 through V lambda m, and I tensor them, I could still embed this in some large tensor power of just fundamental representations. And like in the SL3 case, I get this projection going the other way. And the question I could ask is, what's the kernel of this projection, right? Another way to say this is, well, I have a basis for the space on the left for this tensor power of fundamental representations. Can I say something about which webs here map to 0 under this projection? And are the other webs, like the projections of the things that don't map to 0, do these form a basis, etc.? So that's sort of the goal of clasped webs, is to talk about this sort of arbitrary irreducible representations. And I should remark that in Christian's paper, they do talk about a special case of this. So a special case of these arbitrary irreducibles are the symmetric powers. The symmetric powers correspond to this weight, where you just take a multiple of omega 1. So you don't have any omega 2 or omega 3, you just take multiples of omega 1. And which multiple you take tells you which symmetric power you're in. And they talk about the tensor products of these symmetric powers of V. And they do give a basis for this. And this corresponds to, so this coordinate ring of the Grassmannian has a grading, and the different symmetric powers give you different homogeneous pieces of this. So if you want to understand the coordinate ring of the Grassmannian, you only have to think about symmetric powers. So what they do in Christian's paper is enough. But I want to talk about more, about all the other irreducible representations. Okay, so to really motivate what this non-convexity thing is, I'll take this toy example in SL3 because I think it's easier to picture. So I have these two webs in SL3. So these are invariants of V dual, tensor V dual, tensor V, because I have two white vertices followed by two black vertices. But I could also just as well read these graphs from left to right. So I should think of these as maps from V tensor V to V tensor V, right? But once again, V is my three-dimensional representation. And if I look at what V tensor V is, it breaks down into the symmetric power plus the alternating power. And both of these happen to be irreducible. So the weight for the symmetric power is twice omega 1, so this is not fundamental. But the second exterior power is just V dual. That's, this should be a V dual. I apologize for the typo. But yeah, this is a fundamental representation. But if you know beta rep theory, so you have these two distinct irreducibles, and you want and you have the sum of these, and you want to count maps from the sum of these two irreducibles to itself. Schur's lemma tells you that an irreducible representation cannot map to any other irreducible representation. It can only map to itself, and any such map is just a scalar because I'm working over like complex numbers. So this symmetric power can only map to itself, and the exterior power can only map to itself. And I have two choices for these scalars that I pick. And so the dimension of this Hom space from V tensor V to V tensor V is 2. So I should have two webs, and these are the two webs telling me what the maps are. So the web basis in this case is, there's the identity map, which is the thing on the left, where you don't do anything. V tensor V just maps to itself by doing nothing. But there's this also, there's this anti-symmetrizing sort of map, which is, it takes V tensor W to V tensor W minus W tensor V. That's what this thing on the right corresponds to. Now, what if I want to consider this sort of clasping, where I clasp the two black vertices on the left? So what does that mean? So I have these two black vertices on the left. Both of these correspond to an omega 1 because that's what V is. Clasping corresponds to just adding up the weights. So omega 1 plus omega 1 is 2 omega 1. So when I clasp the two things on the left, I'm really looking at V2 omega 1 sitting inside V tensor V. So in our toy example, what that looks like is, instead of thinking about all of V tensor V, I only look at the symmetric piece in there, right? And then I could ask, well, if I just look at the symmetric tensors and I look at these two maps, what happens to them when I restrict to the symmetric part? So the identity map obviously does the same thing. If you have a symmetric tensor, you could just apply the identity map, you get another symmetric tensor. But This anti-symmetrizing map is more interesting because if I take a symmetric tensor and I apply this anti-symmetrizing map, I'm going to get 0, right? So if I have V tensor V and I apply this map phi to it, I'm going to get V tensor V minus V tensor V, that's 0. So somehow this web on the right is killing the, or is killed by this projection. This projection is coming from restricting any map from V tensor V to the symmetric power sitting in there. So this is sort of what I'm remarking here. So when you project the identity map, you just get the inclusion of the symmetric power into V tensor V. But this other map, if you really think about what it's doing, this anti-symmetrizing map, you're first projecting to the alternating part and then including back into V tensor V. So if you restrict this sort of projection to the alternating part to the symmetric part, that's going to sort of die under this first projection map. And so what's the motto here? So the motto is, well, if you just look at the graphs, what's happening is on the left, I have these two vertices, which correspond to a weight omega1 plus omega1. That's 2 omega1. But I'm somehow trying to squeeze this through the alternating power, which is a much lower weight. So when I try to squeeze the symmetric power through the alternating power, it's just going to evaluate to 0. So this is sort of what the model is any morphism that factors through a low weight tensor product is killed by this projection pi. So this is sort of the motivation for this non-convexity condition that Kuperberg introduces. So this is another way of like depicting what I was just saying. So this identity map, when I clasp the two vertices on the left, this is actually a non-zero thing. But the thing on the right, so this more interesting web, which factored through the alternating part, when I clasp the two things on the left, this becomes 0 because the symmetric part doesn't squeeze through the alternating part. Okay, so this is me just setting up what a clasped web is. So a clasp sequence is just, you just pick subsets of your boundary vertices that you're going to say that you're going to clasp. So this is just telling you where you're drawing the external clasps. And this is just saying that the weight of a clasp is just the sum of the weights of all the boundary vertices, right? So for example, in this picture, I have these two things which are unclasped, so they live in a clasp by themselves. They correspond to weights omega2 and omega2 respectively, the white vertices. The black vertices, like together, live in the clasp with two elements, and the weight of the clasp is going to be omega1 plus omega1, which is 2 omega1. So each clasp corresponds to an irreducible representation, and the weight of that irreducible representation is the sum of the weights of the boundary vertices in the clasp. Okay. Yeah, here's a remark about, anytime I have these clasp sequences, I could just look at the weights of the clasps, and this tells me which tensor product of irreducibles I'm considering. So the weights of the clasps tell me the weights of the irreducible representations, and this is sort of the machinery I'm going to use to talk about bases for these tensor powers of arbitrary irreducibles. Okay, so to talk about, to make more precise this model that I had about factoring through a small tensor power, here's an example of the kind of thing I'll consider. So I start with a web. So this is a clasped web. So I have 3 clasps here. So I'm taking tensor powers of 3 irreducibles corresponding to, the weights that I get when I sum things. But if I start with a clasped web, I could consider any path in here that separates a clasp from the others. So here I'm separating this leftmost clasp from the other two. And I could sort of cut my graph along this red dotted line. And this gives me 2 different webs. So again, I should think of the picture on the right as 2 different webs that if I glue together, I get the thing on the left. And as we saw before, this sort of operation of slicing your graph corresponds to factoring morphism. So I get 2 different maps on the right if I read these graphs left to right. And composing these 2 morphisms is what the thing on the left is. Right? So for this example, the leftmost clasp, I have weight 2 omega 1 and omega 2 and omega 3. So these two middle black vertices of degree 1, they correspond to a weight of omega 1. This hourglass boundary vertex, the thing that's connected to this hourglass, that corresponds to an omega 2. And the white vertex corresponds to an omega 3. So the weight of this whole clasp is, the bottom thing. And for any cut path, I can also associate a weight. And what this actually is you just cut open your graph along this cut path, and then you look at the new boundary that forms, and then you look at the weight of the boundary. Right? So in my picture here, so I have these two semicircles. The weight is just, you look at the left semicircle and you look at the right vertical boundary of this, and then you compute the weight of this. So I have one black vertex, which has simple degree 1, and then I have this one hourglass black vertex, so that corresponds to omega 2. And then I get these two omega 3s. So that's the weight of the cut path. And non-convexity is just the condition that anytime you cut your graph, the resulting weight you get for the path better be larger than the weight of the clasp itself, right? This is sort of going through what our motto was. Our motto was that you cannot squeeze a big representation through a lower weight representation, and these cut paths are basically telling you how you're factoring your morphism. So if this thing is going to evaluate to a non-zero thing under the projection, the weight of the thing on the left, so the clasp itself, better be lower than the weight of the cut path. So you can factor a lower weight representation through a higher weight representation, but not the other way around. And yeah, to be a bit more precise, when I compare these weights, I'm doing it in the dominance ordering on the set of weights, but you don't need to know what that is. But roughly speaking, on the level of graphs, what this is saying is I shouldn't cut through too few edges when I draw a cut path. So the weight somehow is a measure of how many edges I'm intersecting. And for a graph to be non-convex, I should cut through at least as many edges as I have boundary vertices on the left. And I'm just going to go back a bit. If I look at this example, so that's exactly what's wrong with this graph on the right, where I have two boundary vertices on the left in this clasp, but I can sort of cut through vertically by cutting through only one edge. And that's like the cut path has a lower weight than the clasp itself. And that's exactly what went wrong. The graph on the left doesn't have this issue because if I draw any cut path here, it's going to intersect both these edges, and that's a large enough weight for me to be able to factor this representation through. Yeah. So the dilemma now is if W is not non-convex, I apologize for the double negative here, but like non-convex is the word that Kuperberg uses, so we stuck with that. But the point is, if you're not non-convex, so partially convex, then you project to zero. So anything that has cut paths which have low weight, these project to zero under my projection map. And the proof is just saying some Lie theory stuff, which says that you can't factor a high weight representation through a lower weight representation. Okay, so now we have this spanning set, right, for this invariant space of arbitrary irreducibles, because I know that non-convex webs have to span this, because if you're not non-convex, you actually project to zero. So these ones are not important. So if I fix a clasp sequence, I could now ask, well, I have all these non-convex webs. Do these actually form a basis for this invariant space? So these span for sure by the lemma, but are these linearly independent? And the theorem that Christian and I proved is that yes, this is enough. So yeah, what's happening here is I have this invariant space with the v lambda i's. So I take the tensor powers of v lambda i's, and then I want a basis for this tensor space. So what you do is you draw the clasps on your webs, and then you check which ones are non-convex. And the set of non-convex ones are actually precisely the ones that don't map to zero under this projection. And these actually form a basis for this invariant space. And there's this other extra condition that is equivalent to non-convexity, but we don't have a good explanation for why. So this is more like a mysterious condition 3 that we have, which just says that you have no trips that start and end within the same clasp. So this is some sort of generalization of, if you think back to SL2 webs, where Kuperberg talks about U-turns, or like not having any U-turns. So there I only had simple strands. I didn't have these complicated trips, but the generalization of not having U-turns within a clasp is the following: that you don't have trips that start and end within the same clasp. So yeah, what the content of this theorem is, as long as a web doesn't project to zero, so it's non-convex, then this actually is a basis element for my invariant space. So we also have a different combinatorial criterion when our clasps sort of look nice. So if I sort all my clasps, in the sense that within each clasp, the boundary vertices look like the following. I only have these omega 1 vertices, followed by omega 2 vertices, followed by omega 3 vertices, right? So if these aren't all shuffled around, but they just come in the flavor of just omega 1s, then omega 2s, then omega 3s, I call these sorted clasps. And the theorem for sorted clasps is slightly nicer. I have the same conditions as before, where I say that a basis is given by these fully reduced graphs, which are non-convex. So 1, 2, and 5 are the same as the previous theorem. 4 is this condition about the separation word. So this is some condition on the tableau, which is kind of technical, but condition 3 is the more interesting thing, which just says that there's this list of bad local boundary configurations, and as long as your graph doesn't have any of these within a clasp, then you're not convex. And the list of bad local boundary configurations is so I have these 8 configurations, which looks kind of ill-motivated, but if you look at the bottom left thing, this is precisely the U-turn that Kuperberg had. And Kuperberg said that if you have a U-turn within an SL3 web, this is bad. And the same thing is true for SL4, but there's these extra flavors of bad local boundary configurations. And if you look, all of them have this cut path, which I've drawn in this red dashed line, which sort of intersects too few edges. So the U-turn actually has this empty cut path, which has weight 0, and that's definitely smaller than the weight at the boundary. But all these other graphs also have this cut path whose weight is smaller than the weight of the boundary vertices. And this is sort of witnessing the failure of non-convexity. Right? So we have this list of configurations that you just have to avoid. And in terms of trips, I mean, you can also see that each of these bad local boundary configurations has a trip that starts and ends with like the same clasp. So for example, in the top left, if I do a trip 1, I start at this left boundary vertex, I move towards the white vertex, I take a left here, and then I end at this other boundary vertex. So similarly, each of these 8 boundary configurations has a trip 1, which is in green, or a trip 2, which is in orange, sort of witnessing this U-turn sort of condition. So these are 2 different ways to think about why these configurations are bad. But yeah, the point of the theorem is, as long as you avoid those 8 things within any clasp, then your web is non-convex, and the set of these non-convex things forms a basis. Okay, a few things I should say about why this is an interesting basis is this property of this projection. So I had these invariants for just fundamental representations given by unclasped webs, but then I have this projection which does the clasping. So we saw that either these clasped webs map to 0 if they're not non-convex, or the ones that are non-convex, whatever they map to, these remain a basis for my target space. It's actually a very special property. If you have any map of vector spaces and you pick a basis for the first vector space, it's not clear that the things that don't map to 0 under this map should form a basis for the second vector space, right? Even if you have a projection. Yeah, so this this is like a property that's very special to Lustig's canonical basis, and this is like a very difficult to compute basis, but like it has nice properties. So the first like what people hoped for when they first discovered web bases were that these coincided with the canonical basis, which would be really nice. They gives you a diagrammatic way of computing things about the canonical basis, but turns out that this is not true, that the canonical basis is different from the web basis. But it's still nice that the web basis shares this property. And yeah, the other observation from the theorem is that there's this condition about trips. So as long as you don't have trips that return to a clasp, then you're good, then you're non-convex. So somehow this very combinatorially defined trip strands, which a priori have nothing to do with Lie theory. So Christian and I have thought about this a lot, like what are trips actually telling you about morphisms of representations, and there doesn't seem to be like an obvious way to interpret trips, but somehow the trips are carrying just enough information for you to decide whether something is non-convex or not. So this is like a kind of miraculous thing, but we don't have an explanation for why this is true. And a few applications of what you can do with web bases. Web bases are great for computing link invariants, so things like the Jones polynomial, Reshetikin derive invariants, the Alexander polynomial, all of these come from web bases. You can do skein algebra stuff with them. There's applications to cluster algebras, so the Grassmannian, the coordinate ring of the Grassmannian has a cluster structure, and there's conjecturally relations between the web bases and cluster variables for this cluster structure. And once, well, I haven't fleshed out the relation to Young Tableau, but there's this nice rotation invariance that our graphs have because they're drawn on a circle. You could just rotate them. This gives you a promotion operation on the Young Tableau, and you can use this sort of rotation action to deduce things about cyclic seaming, which is cool. Yeah, that's all I had.
Excellent. Do we have any questions for our speaker?
I have a quick question.
Mm-hmm.
Your notion of trips, this still makes sense in the rank in the rank 3 case, right? In
Mm-hmm.
can you use this notion of trips to um, to get at this notion of non-convexity in that case? I mean,
Yes, that's true. So yeah, the way we stated in our paper is uniformly for SL2, SL3, and SL4. So you have the exact same condition of trips not returning to the
uh-huh,
same clasp, and that turns out to be equivalent to non-convexity.
I see. So,
Yeah.
except in the rank 3 case, there's only one. I guess there are two colors of trips, or how many colors
There's
of
two colors of trips. They're
there?
just inverses of each other.
Right.
Like
So
you
that
do a
that
trip. Yeah.
so that's Postnikov's original concept of trip, you're saying. And
Yes.
so
Exactly.
as long as we make sure that those trips don't end in the same clasp, then we're okay. You're saying. Okay, that's nice.
Yes. Yeah. This is definitely a thing Kuperberg knew, but I don't think he explicitly states in his theorem for clasped webs. But yeah, so these strips give an alternate characterization of non-convexity even in SL3 and SL2. Also, you have one flavor of trip. It's kind of silly there. You just follow the strand, but that is
Nice.
just like yeah.
Okay, I also have a quick question. So for your last slide,
Mm-hmm.
you have like this list of like why people like web bases, but like
Mm-hmm.
how in particular are these like clasped web bases? Like these all seem to be like statements about general web bases, but like is anything
Mm-hmm.
about the clasped web bases particular to any of these?
Well, I don't know much about the cluster algebras and cyclic sieving stuff, but like at ICERM, when I talked to certain skein algebra people, they seemed very interested in clasp stuff. Now, I'll have to admit I don't know much about skein algebras, but they think it's interesting. So,
Okay. So it seems like adding this clasp notion contributes to these applications as well. Okay.
yep. Yeah, but I would say the most direct application is to Lie theory itself, because like the motivation for clasping is just, Lie theoretic, like representation theoretic stuff.
Yeah. Okay, any other questions? If not, we can end the recording.